We're continuing in 15.2, and we're looking at gate array logic. Many IC manufacturers produce complex logic systems that can be programmed to perform a variety of logical functions within a single IC. And so using this type of procedure, you would not need to have, your chips that had a whole bunch of AND gates and a whole bunch of inverters and so on. So you would have a single chip that you could program and program it as you see fit. These ICs are known by various names: gate array logic, programmable array logic, programmable logic device, complex programmable logic device. In your text, let's see, your text looks at this particular one right here, the PAL, and we're not going to give a great deal of attention to these, but we do want to at least introduce them. So, gate array logic. Okay, your text has 3 images of gate array logic. Unfortunately, I do not have those images to put in this presentation. You'll need to refer to your textbook. It's in section 15.2. And you have images on 1516A, B, and C. 1516A shows how the chip would actually appear, and if you want to refer to that, please do. You might want to pause the presentation and then turn it back on after you've found the page. This chip, you'll notice it has 20 inputs, and this would plug into a circuit board. Then 1516B, it shows the internal circuitry, and it features fusible links, and these are titanium tungsten that are selectively burned out to create the desired logic. And you'll notice that when they are burned out, these will become permanent, so there is no changing. Now, there are some that are actually programmable, though this particular one, it is permanent. So once you've got to make sure you've got the logic right, because if you don't, you'll have to throw the thing away and start over. Okay, and then 1516C on the following page, it shows how the links have been burned out to program a Boolean expression. And you might note there's 3 inputs, A, B, and C, and you'll see that there is the true and the complement, and the complement here simply means that you've got A, and A naught would be the complement. Note, to create AB, the fusible links for A and B are left intact while others are blown out. So you'll need to look on at this particular 1516C, and if you look closely, you'll see that A and B, they've got the little drawing there, and you'll see where they cross over. There's that little link, and the link is open, and whereas where they're blown out, it looks kind of like this, where the link is broken. So the ones that you would use are the ones that aren't blown out. And you have a special device that when you program these, you put on a special board, you send in the program you want, and it burns the links to create the logic that you need. Also, the outputs use what we call tri-state inverters, and they can be seen on 1516B. And if you flip back to that page, you'll notice there are 1, 2, 3, 4, 5, 6, 7, 8 inverters on the final stage. That's on the far right. And each inverter has an input coming in from the top that allows for enabling or disabling of the output. And so when they are disabled, the output is either it's floating, or sometimes they refer to that as being disconnected. PALs and PLAs are the most basic type of programmable logic devices. CPLDs combine 2 or more PLDs in the same IC package. They can implement, the CPLDs can implement both combinational, and they can do sequential logic as well. And the CPLDs, now often, these are not all of them, but many times they can be reprogrammed, making them ideal for design work. Now the reason this is advantageous may be obvious is because if every time you experiment you have to destroy the chip, that's not really a good thing. So with programmable ones, you can go in, set up your logic. If it works fine, if it doesn't work, you can just erase it and start over again. Okay, so we have briefly introduced gate array logic. We looked at tri-state inverters, and we looked at the PLA that's depicted in your text. And that concludes our brief look at gate array logic.